So the next speaker is also maybe not a really long introduction to most of you because he's also very well known to us. Ceyhun Bulutay from Bilkent University. He did his PhD in Middle East Technical University, and actually there's also another aspect that we actually learned, like how to do quantum many-body systems together. Actually, so we were undergrads together in Middle East Technical University. So he's a long-time friend. And then after finishing his PhD at Middle East Technical University, he went to Santa Barbara, and then he'd been to Essex, and now, starting 2000s, he's now in Bilkent University, and he's been there ever since. So please welcome Ceyhun.
Okay, so thank you, Inanç. I'll talk about our work in several years that has been going on, quantum coherence and control of self-assembled quantum dots. This work has been done by my PhD students, Alikram and Mustafa. They were supposed to be here, but they have a midterm so they unfortunately couldn't attend. First of all, I should acknowledge this event, Alikram Hoca, and we are very much excited, all the quantum optics community, for this Fundamental Sciences Institute. And I hope it will be, we all hope that it will be a very long-lived institute. I will be showing some experimental results as well. It is in collaboration with Sheffield University, especially Evgeny Chekovich. And this is a TÜBİTAK funded research. And this is a short outline. I'll first motivate why quantum dots are good for quantum technologies. And then I'll mention 3 of our studies that are ongoing for quantum dots. And first of all, the atomistic structure using some computation-assisted optically detected NMR. And then for electron spin resonance, our G-factor studies of indium gallium arsenide quantum dots. And finally, I'll talk about our studies on nuclear spin bands and how to quantify coherence in these systems. So quantum dots are semiconductors of low bandgap materials embedded in some wider bandgap materials. These are usually grown by molecular beam epitaxy, and they are quite high quality, and they can be a good representation of an ideal quantum light source. What an ideal quantum light source for quantum technologies is, there should be a single photon possibility, as well as entangled photon pairs. And basically, it should be better if it is deterministic or on-demand. The single photons should be really, there shouldn't be bunching in them. So in G2 measurement, zero delay, they should be as close to zero as possible. And the pairs, entangled pairs, should be indistinguishable by home measurements. Again, this should be a G2 as close to zero as possible. And this brightness should be very high, the entangled pairs or repetition rates. If it's compatible with the existing photonic platforms, that's also very nice. And there should be high efficiency of entanglement as well. I'll just mention standard approach of getting entangled pairs in self-assembled quantum dots. This is through something called bi-exciton-exciton cascade. So when you excite a quantum dot, you generate electron-hole pairs, and they form a bound state called exciton. And if you have a bunch of excitons in presence, they also form their molecules like bi-excitons. So that also has forms a bound state. So starting from a bi-exciton state, by radiative recombination, one of these excitons can recombine and just leave one exciton, and that remaining exciton will eventually recombine, so you'll reach the ground state. And there are two pathways which you can do this through sigma plus first and sigma minus in the second, or vice versa. And if these two paths are indistinguishable, if you cannot, if the environment doesn't know about the path information, then this is really quite, very successful entangled pair. But there are certain obstacles in self-assembled quantum dots. For instance, they are not as nice as these. There is some annealing step, and there is growth kinetics, and this is really not, a pure, cylindrical symmetry system. So any rotational asymmetry gives rise to something called anisotropic exchange interaction, which leaks out the path information. So these two paths are not energetically equivalent. And from the photons, you can understand which path has been taken. So this is something that actually limits. One way of overcoming this is by timing energy entanglement, or by strain, trying to cure this anisotropy or asymmetry in the geometry. Another problem with self-assembled quantum dots is so far, electron spin resonance has been a big problem, and lack of it causes, a lack of full Bloch-sphere control over the system. So that needs to be addressed. And the background nuclei over here, this is 3-5 compounds. So they are all spinful nuclei. So there is hyperfine interaction, and this causes nuclear spin noise. And we need to understand this nuclear spin band to have a good control of quantum technological applications. So first, let me start with our work on atomistic structure characterization. These quantum dots, depending on the growth kinetics, they can be, if they are not capped, pyramidal faceted quantum dots, or truncated pyramids. If they are embedded in some matrix, they are or mostly in the form of lens shapes or some truncated cone shapes, and the inner composition is much of a unknown. Actually, there is some alloying, there is some intermixing between the matrix and the inner core, so it's not just like in gallium arsenide. It's not pure gallium arsenide, but there is some mixing that goes on between the core and the matrix. So one needs to understand what kind of a thing that has been grown. So one way to understand the structure is the way that chemists use a lot, NMR. So like in proteins, for instance. But now we want to use it for a single quantum dot to get the nanostructural information. Here there's a challenge because the nuclear magnetic moment is quite tiny, and at 4 Kelvin or so, under some 3 Tesla magnetic field, the thermal population difference is quite tiny, like 10 to the power minus 4, which is not a problem for chemists because they have in their specimen some Avogadro number of nuclei. So this times this makes up 10 to the power 20 spins contributing to the signal, whereas in a single quantum dot, we have like 100,000 atoms and nuclei. So only about, with this population difference, 10 spins would contribute, so which is a very, very weak signal. So the way to go is actually use something called, like Inanç has mentioned, dynamical nuclear polarization and optical detection of NMR. So which uses, there's a electron in your quantum dot, and through its spin and hyperfine interaction, you dynamically polarize the nuclear spins, and you end up with a far better compared to thermal initialization of population. And for self-assembled quantum dots, this is not good enough. You should do better, and there is actually something called inverse NMR that has been introduced like 6 years ago or so, which has even on top of that 1 or 2 orders of magnitude improvements. This is how the experimental data is taken. Another aspect that is very important in this issue is it's more of a solid state thing. These quantum dots are under strain. This is how actually self-assembled quantum dots are actually grown. So they are intrinsically strained, and this affects the nuclear magnetic environment, because the nuclei are quadrupolar nuclei, like spin 3-half, 5-half, 9-half, whatever. And strain talks to this quadrupolar nuclei through the quadrupolar interaction. So it's the electric field gradient coupling with the spin, nuclear spin. So this is what you expect, a very clean resonances, and this is what you actually get because of strain. But which is good actually, this is a kind of a fingerprint of atomistic structure, so we should actually see this as a benefit, as a blessing. So the computational loop is as follows. You first start from an initial guess of the quantum dot structure, composition, everything, geometry, coming from the transmission electron microscopic data, if available. And then starting with this, you first relax your atoms with molecular statistics, molecular, there are codes like lamps, for instance, which we use here. And then after you relax your structure, you calculate the NMR, inverse NMR spectra, compare it with experiment, and run through this many times. So we have, over the past 5-6 years, tried a lot of structures to see what kind of a composition could really give us the experimental NMR signal. So these are just the lens shapes. These are the cross sections of some lens-shaped quantum dots, only showing the core region. There is a matrix actually around. So the purples are gallium, grays are indium. I don't show the arsenic atoms here. So we tried several structures, core shell, trumpet, or all a ring, on those kind of things, based on some guesses. And this has taken a lot of computer time. And eventually we ended up with some agreement with the experiment. So blue is the computed, red is the measured data, inverse NMR, for the so-called central transition. And there is a very good agreement other than indium 115 isotope, which we suspect is because of some experimental error, possibly in its electric field gradient tensor. That has been actually published in 1970s or so. And the same thing for the broadband spectra. So this is all from 50 to 100 megahertz of NMR signal for 2 spin pumping, sigma plus and sigma minus. This is experiment. This is what we obtained for some structure through computation, and this is their agreement. So more or less we are in good shape in this after 5 or 6 years. Still nothing published so far. On another front, we are also working on G factors of such quantum dots. This is important because electron spin resonance, and G factor is the coupling coefficient between an external magnetic field and the electron spin. And just like in a solid state environment, the free electron mass gets renormalized to an effective mass. The bare the Dirac value of bare electron spin gets renormalized to some value, which is quite important. And this is what we want to find out for quantum dots. Now, this electron spin resonance, there is only one experiment that has been done in quantum dots which claims to have seen electron spin resonance like more than 10 years ago. And this is what they show as the resonance. And look at the transmission, it's just 4 nines or so. It's a very narrow or an shallow dip. And also for another quantum dot like this. So there's a very noisy background, and you should catch this. And they said they couldn't actually reproduce this data. Next day they wouldn't find this dip or whatever. So it's very problematic. Several PhDs were consumed on this, and other groups couldn't reproduce this. And we want to understand what is the problem that makes this electron spin resonance so not reproducible. And for that we want to calculate G factor from an atomistic approach that involves 100,000 atoms of structures that we have identified. Okay, for that we use something that is not so new, goes to last century. It is an atomistic pseudopotential approach, but it's not a self-consistent one. It is just an atomistic approach for nanostructures that has been developed by Ling Wang and Zanger. And this is based on expanding the quantum dot states out of the Bloch states of the constituent elements like indium arsenide, gallium arsenide, and their strained versions. So this is what you calculate, the generalized eigenvalue equation, and you find the atomistic states. And this is for us quite a pain, because when you have atomistic resolution, you find very many states. Most of them are defect states or whatever. So like K.P or envelope function approaches, they would give you very nice envelopes and those things. And we are really trying to filter out all the irrelevant quantum states. So what we have is we are using the G factor expression that has been calculated by Roth in the 60s. And using this expression, we have calculated, using our atomistic approach for freestanding spherical indium arsenide quantum dots, that it scales from the bare value to the bulk value as you change the diameter. So we are now trying to use this also for the lens-shaped quantum dots and see how the G factor is affected by strain and alloy composition. And finally, I'll talk about our work on nuclear spin bath. So we deal with two kinds of nuclear spin baths. If, for instance, for self-assembled quantum dots, it is like you have a electron spin which is talking through a hyperfine interaction to the background nuclear spins in the core or in the matrix. Or in the case of donor centers in silicon, for instance, there is this phosphorus electron which is talking to the spinful silicon nuclei 29, which is actually a very small nuclear spin bath. So we deal with both small and large nuclear spin baths. And the main interaction is hyperfine interaction. So electron spin and the nuclear spins, they talk through the dominant contribution is the Fermi contact hyperfine interaction. So there's an easing interaction as well as spin flip-flop between the center spin and each nuclear spin. So this is how we do. We actually calculate something known as Loh-Schmidt echo. We first start from an initial product state of the central spin, electron spin, and a nuclear spin bed. For the central electron spin, we start from a superposition state of up and down. For the bed, we start from a uniformly distributed coherent spin states, or the Bloch sphere. And they first are in the tensor in the product state, and then as time evolves through hyperfine interaction, the ones that are going with the spin up and the spin down, they evolve with different Hamiltonians, and there is a fork in actually their time development. So there is actually a which way information leaking out to the bed. So whether spin is up or down is kind of imprinted on the nuclear spin bed. So if you just calculate the return probability to this initial state, this is called the Loh-Schmidt echo. And that is a measure of how much there is a loss in qubit coherence if this really diminishes. We can calculate this for quadrupolar spin I analytically, because there is actually just hyperfine interaction and Zeeman interaction, so things are very simple, and there is no many-body physics here. So you can easily calculate the power spectra analytically and find the return probabilities. And what you see is you start from some one overlap, no leakage of information, and there is a collapse and revivals of these probabilities. And we investigate what is deriving this loss of coherence, and we have studied all the parameters in this simple system, like the spin bed size. If you increase the spin bed size from 100 to 1,000, the initial coherence is really very in a short time lost. There's a revival, and the revivals are actually, depending on the spin bed size, also not so perfect. We have also studied the degree of initial polarization. If your initial nuclear spins are not full over the Bloch sphere, but they are kind of polarized, in that case, you preserve the coherence for a longer time, and revivals are better. The hyperfine coupling coefficients, if they are not very narrow distribution, but if they are distributed over a larger region, then the revivals are heavily affected by this. And for different quadrupolar spins, 9/2, 1/2 to 9/2, for instance, we see that if you go from like spin 1/2 to spin 9/2, again the coherence is heavily affected by the spin I value, and we actually have some phenomenological expression that governs all these parameter dependencies. And we have calculated their power spectra, and we have also introduced the quadrupolar interaction, and seen that the quadrupolar interaction, so this quantifies the competition between quadrupolar interaction and hyperfine interaction. So in the quadrupolar dominant regime, we have also a very strong effect of the quadrupolar interaction in negatively in the coherence. We have tried this for two real systems, like silicon phosphor donor system for 100 spins, and usually this power spectrum is in the few megahertz region for different parameters, and for large self-assembled quantum dots, this goes to several hundred megahertz. And all of this was just a single nuclear picture, and nuclei were not talking to each other. They were just talking to the central spin. And then we have started working on the dipole-dipole interaction between the nuclear spins, which makes it a many-body problem. And there we use something called cluster correlation expansion that was developed maybe more than 10 years ago, which accounts for non-factorizable collective excitations within the group. So if you have some nuclear spin and you identify in its neighborhood some other nuclear spin, so there's a dipole-dipole interaction, you just see two-body interactions, and then you enlarge this group, and you try to, you should actually get rid of double countings, and you go to some cluster size, and up to this cluster size like 5 or 10, you do exact diagonalization, and by this means you have a convergent scheme of calculating the Low-Schmidt echo. So there is the Zeeman term in the Hamiltonian, hyperfine interaction, and this is the quadrupolar interaction, which is kind of a squeezing operator actually. And the dipole-dipole between nuclear spins has several terms in it, like Ising term, flip-flops, flips, flops, flop-flop, flip-flip. So all possibilities should be encountered. And this is our one of our last results. So this is now in the kilohertz range, because dipole-dipole interaction is weaker. It affects the longer time dynamics. So for spin 1/2, actually you are in the limited frequency region, and if you go to spin 3/2 or higher, this spectrum broadens. So far we don't even calculate introduce the quadrupole interaction. Here we test what is the cutoff. So by this I mean you introduce some cutoff in your calculation beyond which you do not include any dipole-dipole interactions. So if there should be convergence in this as well. So you test what is its effect, and you see that when you increase this cutoff to larger and larger ranges, you actually get a better resolution for the lower frequencies, okay, which is kind of expected because their dipole coupling is of a smaller strength. This is a zoom into the frequency window between 4 and let's say 7 kilohertz, and if you increase the spin batch size, you see that these reds to blues, there is a continuum nuclear spin noise spectra becoming more continuous with all the subharmonics and harmonics through interactions. So this becomes really a continuum of noise spectrum. And this is now having the quadrupolar interaction in the Hamiltonian. This one without, the red is without any quadrupole interaction, and blue is 10 times that of the dipole-dipole interaction. So we see that the spectrum broadens by the presence of the quadrupolar interaction from 50 kilohertz for this case to much beyond 150 kilohertz. So we are working on this. This is what we have so far. We have developed certain computational tools. One is for identifying the quantum dot structure, for checking with optically detected NMR, and we are currently working on the G factors of indium gallium arsenide quantum dots from an atomistic level. This is the technique that we are using, and we are also trying to understand the nuclear spin batch coherence or decoherence and how to control it through dynamical decoupling regimes. And this is the technique that we have implemented for this. Our main motivation was to understand this solid-state system from a quantum optics perspective, but they are also useful for building, maybe not nuclear spin memories, and quantifying optical write-in, readout, and if ESR, we have a better understanding on ESR, they will be possibly useful for rotational operations on these quantum dots. Okay, so with that, I thank you all.
Regarding the option echo to decay, I think you see only the Gaussian decay, right? That is supposed to be for short times, and then used to be in another life I was working on this. You then tend to see this Lyapunov regimes or golden rule regimes and so on. Do you also see those? Or?
No, this is not in our model. You're right. Yeah. So we don't see any non-Markovian regimes, or this we are seeing just a Gaussian decay in this model.
So the Gaussian keeps on Gaussian.
Yes. Yes. That's a limitation of our model.
There are no more questions. Let's thank all the speakers of the session.